Right, okay, so hello everyone. So I am Simeon of Carnegie Mellon, and I'm going to talk to you about the kinematics of damn Lyman-alpha systems. This is work I've done with Martin Hainault, who is sitting over there, Marcel Niedermann, and a large fraction of the repo team. Okay, so for those of you who weren't in the earlier talks, what are DLAs? So these are very strong neutral hydrogen absorbers. They have a column density around 2 × 10 to the 20 atoms per centimeter squared. That's their definition. Their density in atoms per centimeter cubed, their spatial density, is about 1/10 of the star-formation criterion. So these are nearly star-forming gas. They're dense and they're neutral, and they inhabit, moderately sized galaxies. And here's a picture of one just there. So what hosts these things? So it's been known for a while, I think, and we showed explicitly for our simulations in this paper, that you can match the number density and the abundance and the metallicity of them with halo masses between 10 to the 10 solar masses and 10 to the 11 solar masses, so a little bit small halos. This is the DLA metallicity. You can see that it's somewhat less than solar. This is good. But there's been for a number of years a problem with the velocity dispersion. So if you look here, this is from Andrew Ponson's simulation in 2008. And this is the simulated result. And these are what you see observationally. So this is roughly the virial velocity of the host halos that you're tracing. And you can see that he doesn't get quite enough very, very large velocity systems. And his peak is not quite in the right place. So the velocity dispersions of these the velocity dispersions of DLAs were historically not quite matching the observations. So one way that you could maybe solve this problem is by increasing the size of the halo mass that hosts DLAs. I'm going to try and tell you, kind of the punchline of this talk is going to be that this is not actually totally necessary. So how do we measure these things? So the neutral hydrogen line here, the Lyman-alpha line, is extremely saturated. So instead of the Lyman-alpha line, you use metal lines. This is a metal line spectra. This is a simulated spectrum of silicon-2 that I've pulled out of a simulation. We're measuring the velocity dispersion by looking at this thing, which is the velocity width, which was defined in a paper by Prochaska and Wolf in 1997. This is defined to be 90% of the total integrated optical depth across the absorber. So the idea here is that there's not much absorption here and not much here. And the rough size of the absorber will be the region given by 90% of the integrated optical depth. And this will somehow correlate with the halo virial velocity. At the moment, I'm just going to assert that it correlates with halo virial velocity. I'll come back to that later, and I'll show you that it does. You can take a bunch of these spectra, and you can find a histogram of their velocity widths. And this is what you get. And I'm going to come back to this plot later. So for now, just take that this is the velocity width down the horizontal axis, and this is the histogram. This red line is my favorite simulation. And these points here are binned data points from Marcel Niedermann's sample. And these gray bands here are measurements of the error. So these are bootstrap errors. What I've done is I've taken a sample like the data sample from the simulations, and I've put a region which encompasses 68% of the samples, and I've marked that on the plot. So what this is the probability of getting this data from the simulations. And you can see that, yeah, I think it's in pretty good agreement. I'm going to claim that, yes, this is, all these data points lie more or less within the 1 sigma boundaries of the model, which is nice. This blue line here has the same physics as the red line, but a somewhat worse resolution and a somewhat larger box. So you can get some idea of how well converged we are in the worst case by comparing the blue line to the red line. Yeah, that's reasonable too. Okay, so I have produced a nice agreement. How did I do this? Okay, so first, the boring details. I ran a cosmological hydro simulation with a 25 megaparsec box for the large simulation and a 10 megaparsec box for the high resolution simulation. I fire sight lines at random through the box, until I get 5,000 sight lines containing a DLA. Because the box is relatively small, I had to fire a lot of spectra through the box. There's about 1 DLA in maybe every 100 or 1,000 spectra even. The more interesting question maybe is, how did I do this where other people didn't get this? So there were 2 ingredients that I thought were particularly important here. The first is the way that the shielding is done from the ionizing background. So gas at these high densities is shielded from the effects of the ionizing background and becomes neutral. The second one is the details of the stellar feedback model, which affect the result. So let's go into the first one first, because it's simpler. So this is a plot showing the neutral fraction of hydrogen of different densities in the IGM. This is from Ali Ramati's paper in 2013. You can see that this line here is the optically thin result. So this is what happens if you ignore self-shielding. And you can see that at a certain density, maybe 10 to the minus 2 atoms per centimeter cubed, self-shielding kicks in and the gas becomes mostly neutral. This is the DLA density. So the exact details of this transition don't matter a huge amount for this. What matters is that above a critical density, you're neutral, and below a critical density, you're more or less ionized. And this critical density is roughly 10 to the minus 2. So what matters is the position of the critical density, not the exact details of the transition to first order. But we're not looking at neutral hydrogen here. We're looking at silicon. We're looking at metals. So you have to find some way of prescribing the way the self-shielding works for the metals. This is what I've done. So this red line is the neutral hydrogen fraction, and the green lines are the fraction of silicon in silicon 2 at different temperatures. So 10 to the 4 Kelvin is 20,000 Kelvin. In practice, most of this gas is much nearer to 10,000 Kelvin than 20,000 Kelvin. I have checked this. The self-shielding factor, so the self-shielding is implemented by reducing the photoionization rate at high densities. So the UVB is attenuated. You don't get so many ionizing photons. I do the same thing. I fire up cloudy, and I generate a bunch of density ionization models for silicon with an ultraviolet background, which is attenuated by a factor the same as the factor that we attenuated it for neutral hydrogen for all energies greater than 1 Rydberg. So for all energies less than 1 Rydberg, it's the same as it would be in the optically thin case, which means that you don't get, for example, silicon 1 forming. For high energies, it's attenuated by a certain amount, so you get more silicon 2. You can see here that there is a high fraction of silicon and silicon 2 at a somewhat lower density than there is for neutral hydrogen. This is because the ionization potential for silicon 2 is 16.3 eV, which is greater than 13.6 eV for hydrogen. So the effect of this is that the clouds of silicon 2 are a little bit larger than the clouds of neutral hydrogen, which increases the velocity dispersion and somewhat improves agreement with observations. So that's one effect. The second thing that's going to be important is the way that the stellar feedback is implemented, so the way the energy from star formation back reacts on the gas. This is the detailed model that we've been using. I'm just going to go through it a little bit in case some people are not familiar with it. So the way this works is that each star will drive outflows. The outflows will have a velocity proportional to the circular velocity of the halo in which they find themselves. This is designed to produce a high mass loading in very small halos, and so the star formation gets suppressed more, and so we can better match the stellar mass function at the low end. These are particular parameters we're using. The thing you have to remember is that the outflows in the small halos are slower, but they push out more gas. Obviously, there are some free parameters here. This is one free parameter. I have changed some of the free parameters to see the effect that we're having. So we have a few models. Here we have no SN, which has no feedback, or no effective feedback. This is the thing I just described to you. Here I have increased the speed of the winds by about 50%. So it's exactly the same as this model, but this 3.7 is replaced with about 5. This model, I've just made the winds have a constant velocity. This does not suppress star formation at the faint end very well. And then this fifth model, which is the same as 2, but with a higher resolution. Okay. So what does this do? This changes the virial velocity of the host halos. This is the virial velocity of each halo hosting a DLA in our sample. And this is a PDF. you can see that the default model has halos with a virial velocity less than 40 kilometers per second have been prevented from hosting DLAs. As James mentioned earlier, 40 kilometers per second seems to be an important number. So instead of the peak characteristic virial velocity of DLA hosting halo being about 30 without feedback, it moves up to about 60 or 70. And if I show you again the distribution of velocity widths, you can see that actually they track each other quite well. So here we have halos with virial velocity of maybe 70, 80 kilometers per second, and they produce DLAs with a velocity width of maybe 70 to 80 kilometers per second. Without feedback, you get DLAs with a virial velocity of maybe 30 kilometers per second, and again, the velocity width is about 30 kilometers per second. And this one where the winds are a bit faster is intermediate. This model, which doesn't suppress DLA formation in small halos very well, has, again, too small a velocity width. So it does seem that these are basically, they're probing the same physics. This quantity is telling you something about the virial velocity of the host halos. One thing that you should note is that, as Ryan said, the DLAs form in a very large variety of halos. So there are both very small halos with maybe 30 kilometers per second virial velocity and very large halos with maybe 200 kilometers per second. So this is a wide range of things that we're seeing here. You might want to check, you might want to ask yourself, even though on average the velocity width and the virial velocity are about the same, for individual halos, how do they correlate? And the answer is relatively well. So this is the virial velocity the velocity width divided by the virial velocity, and you can see that it's centered on 1 for my preferred model, but it has a very large scatter. Partly, this is just because if you happen to intersect a halo offset from the center, you'll only see a partial part of the annulus. These other models here this is the result from the simulations done by Hainaut, Steinmetz, and Rauch in 1998, which is relatively similar to our simulations without feedback. And this is the results of a semi-analytic model I made assuming a disk. One other thing you might have noticed in these two plots is that this one stops at about 200 kilometers per second. This one does not. This one has some spectra with maybe 400, 500 kilometers per second in it. How does this happen? It's very strange to have halos that have velocity width significantly greater than the virial velocity. The answer is that while up here, you can get you get DLA spectra that trace the virial velocity, down here you tend to get two absorbers aligned along the line of sight. So here's an example of this. This is a spectrum that has been fired through two absorbers. This is the neutral hydrogen density, and this is the silicon density. So you can see there's a DLA just here, and here there's a Lyman limit system. And again, this has some metals in it. This has more metals in it. So that's how we're getting these very large velocity widths here. You're firing it through two absorbers, which happen to be connected. There's also a correlation here between the virial velocity, between the velocity width and the metallicity. This is a mass-metallicity relation because the velocity width correlates with the virial velocity, which correlates with the halo mass, which correlates with the metallicity. So this is a velocity width. This is a mass-metallicity relation. It has been observed at redshifts 2 to 4, and I can report that yes, our simulations do indeed match it. If you run a bunch of statistical tests on the results, you see that they're in pretty good agreement. So that's great. So just to conclude, we can match the DLA velocity widths now. This is very good. Couldn't do that before. We can also match the correlation with metallicity, which is a nice check. None of these simulations were tuned explicitly to match this. It was tuned to the star formation history, so that's nice. The DLAs are still in relatively small halos. We've done this two ways. Firstly, we've allowed silicon-2 to form at relatively low densities by adding self-shielding. And secondly, we've had strong feedback, which has enabled us to suppress DLAs forming in halos with a very small virial velocity. And those were the leading order effects. Thank you. Hang on. Let me show you. OK, let me go back to this. OK, so if you don't have, so part of it is that even if you, part of it is actually a coincidence that it works so well without supernova feedback. If you don't have supernova feedback, you get very, it's beeping a bit, you get significantly too many stars forming. So you get significantly too many metals. So then it becomes a little bit easier to have actually a large velocity width because you're always going to be intersecting some kind of stars. So partly that's a coincidence, I think. Partly, I think it's because you're seeing a velocity structure, and you might naturally say that, you know, if something is bound to a halo, it's going to have something characteristic of the halo virial velocity, and I think it's just that. You know, if something falls in from this side with a certain velocity, which is roughly given by the potential, and something falls in from that side with a provided you're consistently getting a whole bunch of clumps. And when, in the absence of supernova feedback, you do consistently get a whole bunch of clumps. Because everything clumps. There's nothing to stop it. And with supernova feedback, you get a whole bunch of gas for a different reason, because the outflows are blowing it out everywhere.
So we know a lot of things about damp Lyman-alpha systems and their metal line counterparts. So let me just mention 3 that you didn't explicitly discuss and see whether you've looked at them and what your results were. At redshift 3 and above, they cover the entire sky, that is the damp Lyman-alpha. So if you're looking at a quasar above redshift 3, you've got a very high probability it's going to intersect the damp Lyman-alpha system. This requires very large neutral hydrogen. And so are you seeing that? Question number 2, as Prochaska and Wolf showed, there's a particular velocity structure in the metal line system, for example, the edge leading effect. And you should have been able to see that if you're seeing all these metal lines. And question number 3 is that if you look at the higher ionization systems, like carbon-4, they have typically much larger velocity widths for the same halo. Are you seeing that?
OK, so I think you actually asked me some. I think you might have asked me these questions last time I gave this talk here.
Because those are the key questions.
Because they're very important questions.
It's great that you're doing so well, but now I want to push you and see if you're doing the other things.
But I was forewarned this time, and so I made backup slides. OK, so let's take the first question first. So this is the neutral hydrogen abundance. And the answer is that yes, you get it up to redshift of 3. Below redshift of 3, we get too much neutral hydrogen. I think this is, I think, a factor of the fact that we're not
doing enough recombination?
No, I think it's a fact that the feedback isn't quite strong enough. We're actually having slightly too many stars at this low redshift as well. And it's not, you know, it's a factor of 2, which is.
How do I see from this that you have enough covering?
This is omega.
Well, so that you're reproducing the observed abundance of DLA.
Yeah, I can also show you this if you want. This is the quantum density function. So yeah, we're reproducing the observed abundance of DLAs. So yeah, that's the first one. The second question is a bit more tricky. And the third question I'm not going to answer because I haven't looked at that yet. That's for the next paper. The second question is the edge leading statistic that you asked about. So one definition of this is the difference between the velocity of the largest peak in the spectrum and the mean velocity. Let me just find you a spectrum. Right, so in this case, this is the velocity width. The velocity peak is here. This is the largest peak. And the mean velocity is the midpoint between the left edge of velocity width and the right edge of velocity width. Right, so this statistic is the difference between the peak velocity and the mean velocity in units of velocity width. This is what we get. Okay, so this is a somewhat interesting question. This is the data. And each of these lines is a simulation. You can see that the simulation without feedback does extremely well. Like, it goes right through the data points. The simulation with feedback does somewhat less well. Like, we're getting too many simulations with where the peak is significantly offset from the center of the spectrum. It's not clear to me whether this is really significant. If you do the bootstrap errors on if you do bootstrap errors on the simulated sample, then you can see that these things are like inconsistent at 1 sigma. That's really inconvenient because I can't say, oh, this is fantastic, this agrees really well, but equally I'm not sure that I wouldn't bet my life on this not just being statistics. If you were to take it seriously and wanted to guess what is wrong with the model and how you can make the model better, I would say that we're pushing gas out at like a particular velocity. And that velocity maybe the fact that all the feedback is going into pushing gas out at a particular velocity could be leading to some kind of forcing term which creates a very high peak at a particular velocity. So maybe you need to just make the model a little bit more complicated. Maybe you want 2 velocities, or maybe you want some thermal feedback in there or something. That would be my guess. But like I said, this could just be statistics, and I wouldn't bet my house on it.